I have something.
Recording problem.
So, okay. Okay.
Message is jumping out.
Okay. So in this talk, I will tell you about our new multi-well phase field model for the transformation in titanium alloy. It will join work with Ondřej Souček from the Mathematical Institute, Jiří Kolbík from the Department of Physics of Materials from our faculty, and Jindřich Dobřanský and Stanislav Tuchtyk from the Institute of Industrial Technology of Polish Academy of Sciences. So I will start with the motivation, but the whole talk will be about the model and how it works. So metastable alloys, such as titanium alloy, can exist in different phases. Typically, phases are called beta, omega, and alpha. And after the quenching of the beta phase, the material slowly transforms eternally into the omega phase. And the omega phase is important for us because it is the precursor of the alpha phase, which says if the material will be stronger at that place when it's the alpha phase or not. But here we are mainly interested in the transformation beta to omega. The omega particles are typically small, several nanometers, and what is very important, they can never touch. And the model we developed, so the main advantage of this model is that it prevents of touching of the omega particles. Here in the picture on the left, this is the picture from the transmission electron microscope. So here you can see the beta phase in the cubic structure. Here is the omega particle in the hexagonal structure, and the transition from beta to omega is perfectly diffuse. There is no sharp interface. So, yes. So here in this animation, you can see in the atomic level, so how the atoms are moving as we transform from the beta cubic phase to the omega hexagonal phase. So what happens? The cube is elongated. In the diagonal, and simultaneously with this, parts of the atoms are collapsing into one common plane. So such transformation is not affine. So that is why we are not able to model exactly the cubic to hexagonal transformation. So we do it in a very approximative way. So we say we forget about the collapse into the common plane, and we take just the transformation of the cube of the elongation. So this transformation is the cubic to trigonal transformation. In this case, there are four possibilities. You can elongate the cube in this diagonal, this diagonal, this diagonal, and this diagonal. So altogether, there are four possibilities how to transform beta. So that is why there are four possibilities of omega variants. On the other hand, the problem with this is that if you take this real transformation beta to hexagonal structure, so this transformation does not enable that two different variants of omega will touch together. On the other hand, if we assume just the cubic to trigonal structure, so it is possible from the continuum mechanic point of view that they will be in touch. So somehow we need to add some additional information to prevent the contact of different variants of omega. So after this motivational introduction, so I will start with the model. I already said that the transition from beta to omega, or even omega and omega, is perfectly diffuse. So there is no sharp interface. So that is why we are modeling it using the phase field method. So typically in the phase field method, every phase is described by the order parameter eta. In our case, it is the real volume fraction. So if we are in one phase, the volume fraction is 0, meaning that it is absent. If it is equal to 1, it means that it is present. Typically, in the phase field method, we prescribe the free energy density, which consists from two parts. the interface energy density that says how the material stores the energy in the interface, the diffuse interface, and the dark part, which is typically responsible for the elastic energy, chemical energy. But in this talk, I will mainly speak just of the interface energy, and the aim of the model is really to prevent the contact of two omega particles. And then the evolution of the volume fraction eta is driven by the Ginzburg equation, saying that the time derivative of eta is proportional to the chemical driving force, to the thermodynamic driving force. So this is just the functional derivative of the free energy with respect to eta, and the constant n is the mobility. So the Ginzburg equation and the free energy can be reformulated by adding the dissipation potential, which is in this case just in this quadratic form, and the Ginzburg equation can be then formulated as the functional derivative of the dissipation potential with respect to eta dot plus the functional derivative of the free energy with respect to eta equals to 0, and this is what we will use in the whole talk. So in this case, I'm just speaking at the beginning just only about two phases, but as I said already in the motivation, we know that we need to describe 1 beta and 4 variants of omega. So altogether 5 phases. So I will start with 2 phases, which is known, and it is clear what to do with this. So in case of 2 phases, the most popular interface energy is called WL potential. It consists from 2 parts, from the gradient part and the algebraic part, and the name of the potential is named after the algebraic part. So it is a WL with 2 minima, 0 and 1, and the gradient part makes the transition from one phase to the other phase. It contains 2 material parameters, the interface thickness parameter L and interface energy density, gamma. So as the name suggests, so the interface thickness parameter L says what is the typical thickness of the diffuse interface, and interface energy density is really the energy density. So if you, in one dimension you minimize this, so this is the same sign, it is the same. If you minimize the total free energy in the whole space, so gamma is indeed the interface energy density, meaning that at the minimum, the gamma is then the density of the energy. And the equilibrium shape of the interface is the hyperbolic tangent. So if we go with the here I can plot beta with respect to psi. So it is this formula. 1 plus hyperbolic tangent, so it's 1/2. So here at 0 there is interface. It is exponentially going to 0. If we go to minus infinity, and if we go to plus infinity, it goes to 1. So this was just 2 phases and the interface energy. So I will repeat it again and again. What is the aim? The aim is to get a model for n plus 1 phases such that it prevents the contact of 2 variants of omega. So we start with this ansatz. So we use the diagonal term of the interface energy for n plus 1 phases. So we have now n plus 1 volume fractions, eta 0, eta 1 up to eta n. And in every space of the material, there can be only just one material, so it means that they have to sum up to unity. In the whole modeling part, we assume that we have just 2 families of interfaces. Either we have interface between some different variants of omega, or we have interface between beta and some omega. So to this corresponds the interface energy densities gamma beta omega and gamma omega omega, and interface thicknesses gamma beta omega, L beta omega and L omega omega. So first thing we want to do, we want to have something we call algebraic consistency, meaning that if we think that only two phases are present in the system and all other phases are absent, we want that it reduces to the standard double well model. So we start with only n equal to 2, meaning that we have three phases, 1 beta and 2 omegas. And in that case, we can find a relation between the material parameters, kappas. I will repeat, kappas are the material parameters in front of the gradient part, and epsilons in front of the algebraic part. So we get the following relation. So kappa 0, 0 is related to gamma, beta omega, gamma omega, L omega, omega, and so on. And if we have n plus 1 phases, so not 2 plus 1, but n plus 1 phases, we can again get the relation for the parameters. So here it is not clear that you can get the relations. You can get it here only because we have really just two interface families, no? Beta omega and omega omega. Otherwise, it is not possible to solve the system of algebraic equation to get the relation between kappas, epsilons, and the real physical material parameters. This is important for us because from some measurements we can know or at least well estimate the values of gammas and L's. So this was the energy. The other thing is the dissipation potential. So in the Ginzburg now for two phases only, the dissipation potential was just quadratic in the time derivative of the volume fraction. So here we have a sum of the quadratic terms. And what we do first, we reduce the system. So we express everything just in eta 1 to eta n from the information that eta 0 is 1 minus all eta I from 1 to 1. So if we do it, we can transform the dissipation potential and the interface energy. So the dissipation potential expressed just in eta 1 to eta n is in this form. So it is in this nice matrix form. So you can see on the diagonal there is always 1 over m0 plus 1 over mi, and everywhere out of the diagonal there is 1 over m0, and similar it is in case of the interface energy. So for the gradient part, there is again this matrix form. For the algebraic part, we cannot do much with this because it is not linear. So we can just substitute for eta 0. So now we have some physical constraints. The first physical constraint is that we want the second law of thermodynamics is satisfied, meaning that the dissipation, which we can compute from the dissipation potential, since our dissipation potential was quadratic, so dissipation is just dissipation potential multiplied by 2. We want that the dissipation is always non-negative for all possible intervals. This means that the matrix, we call it here M1, has to be positive definite. Similarly, we want that the interface energy is bounded from below. So it does not go to minus infinity. And if this matrix would be negative definite, we could easily go to minus infinity because we can scale in the space, the gradient terms. So it says that also the other matrix, so here it has to be positive semi-definite. Now I will just, so what we will do, we will write down the Ginzburg equation that we have in the form, I will repeat it here, the functional derivative of d with respect to eta I dot plus the functional derivative of the free energy with respect to eta I equals to 0. So we write it down, we can write it in this vectorial form. So we apply the matrix M1, this was in the dissipation potential on the vector of the derivatives of the volume fractions. This is on the left hand side. On the right hand side, the gradient part creates this part, and then there is a part coming from the algebraic part of the free energy. And So this we can just write in this way. So now what we do, we want to express the etas dot, and we have just a simple evolution equation. So we multiply this equation from the left by M1 inverse, and we get this involuntary equation. So now we have some simplification. So I will repeat. We want it for M1 that it is positive definite to satisfy the second law of thermodynamics, and for M2 to be positive semi-definite to have the energy bounded from below. So I do not want to comment it more in this talk. So what we just say that M1 is related to M2 just by some positive constant. And if we do this, we can easily compute what is M1 inverse times M2, and we get this evolution equation for the volume fractions. And now comes the other condition we want from our model. So the first condition was the algebraic consistency. I will repeat it. We want it from the model that if only two phases are present in the model, it reduces to the standard two-dimensional tableau. The other thing, so this is something that was stated in 2006 by Boyer, is evolution consistency. So he said if a certain phase is not present at the beginning, it should not appear spontaneously. He did it for three phases only. We need more than three phases. So for this titanium alloys, we want 1 plus 4 phases. We are also thinking about some sub-variants. So finally, it will be 1 plus 12, meaning 13 phases. And to do exactly what Boyer did in 2006 is very difficult if you have more than 3 phases. So that is why we relaxed this consistency, and we said that if the multi-phase model reduces to 2 phases only, model, so none of the absent phases emerge spontaneously. So we have just 2 phases, and all other phases are absent. They cannot appear just by themselves. Also, this is a relaxation of this, and of course, in case of 3 phases, it's exactly equal. So now we want to check our evolutionary consistency, and we do it on our model. So this is the governing equation for the volume fractions. So first of all, so we consider also I will then repeat. So here. This is obtained after we substitute for eta 0 is equal to 1 minus eta 1 plus eta 2 up to eta. So it contains only unknown eta 1 to eta. So if eta k is not 0 and all other eta k's are 0, it means that eta 0 is 1 minus eta k. So there are just 2 phases in the model, and our relaxed evolutionary consistency says that we want that the phases that are 0 at the beginning, they do not appear. So now we forget for the analysis about the Laplace term. We will think just about the algebraic part. So this means that if eta k is not 0, so we want that only eta k is evolving and all other are not evolving. So this means that on the for the component k or j. Different from k, we want that the right-hand side is 0. Otherwise, it is not 0. So this means that this term is to be proportional to ek, which is the vector where there is 0 on the component different than k, and it is equal to 1 on the component k. And this thing coming from the algebraic part of the interface free energy after substituting for all eta k's different than k 0, we get this relation. So if we insert it into the inverse matrix, we obtain such a such a formula. No? So this can be easily checked. Oh, I skipped. Okay, sorry, I skipped one slide. So it is easily checked after this. So so to compute an inverse. So to compute an inverse, we use the Sherman-Morrison formula because in fact the matrix M is just the rank one perturbation of the diagonal matrix. No? So this is diagonal matrix where on diagonal we have kappa 1 to kappa n, and then we have a matrix. Then we have a matrix where all components are equal to kappa 0. So the Sherman-Morrison formula looks like this. We have some matrix A plus U tensor product B, and the inverse of this is computed as A inverse plus this term. For the diagonal matrix, you can easily compute the A inverse, and this matrix can be computed, can be written as the tensor product of kappa 0, vector of all kappa zeros, and vector of all ones. So if we insert it here, we can easily compute that M inverse is the inverse of the diagonal matrix plus this part. And now if I use this on the next slide, which I accidentally skipped the slide. If we take this vector and this is the matrix M inverse multiplied by this vector from the right, we get that the M inverse applied to this vector equals to this. And we want that this is proportional to EK, this result. Here is EK, but here is something which is not EK, so there are some non-zero entries, for example, on the left in the component J different from K. So the thing what we want to make this 0. So we want to make epsilon 0 over kappa 0 equals to epsilon divided by kappa K. And if we substitute for the relation between the kappas, epsilons, and the interface energy densities and thicknesses, we get that if we want to satisfy the evolution consistency condition, the thickness parameters have to be same, all of them. So this is something that we believe Boyer was not aware of, because unfortunately in this model he did not allow to have different thicknesses. So for him it was for free. Also every so this is known for free phases. This is Boyer 2006, Boyer 2006. So now I will come to the limitations due to the positive definition of the matrix M. So I will repeat it. We want that the second law of thermodynamics is satisfied, and we want that the interface energy is bounded from below. So the matrix M, which looks like this, we want that it is positive definite. And if you check what it means, assuming that all interface thickness parameters have to be the same to satisfy the evolution consistency, we find out that we have the relation between the interface energy density between two variants of omega and interface energy density between beta and some variant of omega. It looks like this. And in our case, when we are interested in beta and 4 variants of omegas, it means that gamma omega omega has to be less than 8/3 times gamma beta. So now comes the new thing. So we want that 2 variants of omega will never touch. This corresponds to something which is in literature called total spreading case. It is not. In some cases, it is usual. For example, in martensite transformation, chain memory alloys, where we have austenite and several different variants of martensites, this is completely different words. It is not true that the total-spreading case is valid there. And here, as you can see in the animation, at the beginning, we have 2 variants of omega, omega 1 and omega 2. And here is beta phase. And we never want that 2 omegas are in contact, because on the atomistic level, it just does not fit. So the atoms transform in a bad way. So in fact, we want that it is energetically more preferable to put beta phase between the different omega variants of omega. So how to do it? So this seems quite easy. So the interface energy between beta and omega 2 is gamma beta omega. Between beta and omega 1 also gamma beta omega, the density, and between two different omegas it is gamma omega omega. So the idea is quite easy. If we make gamma omega omega just 2 times larger, more than 2 times larger than gamma beta omega, it will be more preferable to create two phases, two interfaces between omega 1 beta, beta omega 2, than to have directly omega 1 omega 2. Unfortunately, what then happens is that the first parameter in front of gradient theta 0 square in the interface energy is negative. If it is negative, so we don't have, and all other kappas are positive, so of course we don't have the positive definiteness for free. So we need to compensate negative kappa 0 by large enough kappa 1 to kappa n. This is this condition. If you implement it in the way that you use just gamma omega omega, for example, 2.1 times gamma beta omega, it works fine before you add the chemical energy. So up to now I was just speaking about the interface energy. In the model, we need to also add the chemical energy, which says that what phase is energetically more preferable. So in case of the beta to omega transformation after the quenching and the thermal transformation, the omega variants are more preferable, which means that the difference between the chemical energy omega minus gamma omega minus gamma beta is negative. So beta is more preferable than omega. So what was shown here, it works fine if it is positive, but this is not interesting for us. And so to fight with this, we need to increase the ratio between gamma beta omega and gamma omega omega even more. For example, we would need the gamma omega omega is at least 5 times gamma beta omega. But we cannot do it because we have the restriction on the positive definiteness. It stops working. So we need to solve it in different way, and this is the new part of our model. So the best thing how to play with the energies is to use the ternary plot. So in the ternary plot, we have a triangle. Every corner of the triangle has a meaning. So this corner means that we have pure omega 1 variant. This corner, if we are in this corner, we are in the pure omega 2 variant. If we are in this corner, we are in the pure beta phase. So now, assume that gamma beta omega is 0.01 and gamma omega is 2.2 times larger, which satisfies the condition that it is less than 8/3. Oh, and this is here it is not 8/3. We have just prepared it, so it is even less, but even that is satisfied. And we have no chemical energy, and as I said, then it works. So this violet line is the line which is connecting the pure omega 1 variant and pure omega 2 variant. And we are going in the valley of this energy landscape. So if you go in the valley, so you are going almost to the beta, and then from beta you are going to omega 2, which is exactly what is shown here. The total spreading case says that if you want to go from omega 1 to omega 2, you need to go through beta. So now what we will do in this experiment, we will increase, in our case decrease, we will increase the absolute value, but we will make the delta G, the chemical energy, more negative. When it is minus 0.007, so if we go from omega 1 to omega 2, you do not go directly from beta, but you go a little lower. If you decrease the chemical energy even more, you have a direct interface between omega 1 and omega 2. So one possibility would be, really, as I said, to increase gamma omega omega. Again, I repeat, we cannot, because we would not satisfy the positive definitions. So we need to modify the model, and we modify the model by something we call double ditch. I will show again the ternary plot. So we call it double ditch, in Czech dvojkorítko, because we add one ditch on this edge between beta omega 1 and one ditch on this edge beta omega 2. So this is parabola like this and parabola like this. And in fact, what we get a big hill between omega 1 and omega 2, which will make not preferable to go directly from omega 1 to omega 2. So you can think about this also about the tent. You have a tent, so here it is fixed to be 0 on this edge, and here is the tent open. So this is exactly this tent. So we add all combinations eta I squared, eta j squared, where ij are greater than 0. And of course, adding this term will destroy our evolution consistency condition. But it will destroy it only on the edge gamma omega omega. So what it means? It means that it will kick away. So if it happens that the point in the material is on this edge, directly on the interface omega 1 omega 2, it will kick it away towards beta, and it will not stay there. And this relaxation of the evolution consistency is exactly what we want. We never want to be on this edge. And of course, then in our test, we did the thing that initially we put some points on the edge, and we want to disappear and get away. So here we have the coefficient, the double ditch lambda parameter, which is positive, and making it larger, we make the hill between omega 1 and omega 2 bigger and bigger. Okay. So we will continue with the test. So here we ended. So we made the chemical energy equals to minus 0.02, big enough. And if there is no double ditch, we have a direct interface between omega 1 and omega 2. So we check what happens if we increase it to 0.2, so it is good. So in the energy landscape, we want to go from omega 1 to omega 2. We go closer to beta, not so far, but by increasing lambda to 5, we go, the hill is very huge. You can see it also in the colors. So if you want to go from omega 1 to omega 2, you need really to go very close to beta. Also, as I said in the beginning, we want that the algebraic consistency condition and the evolution consistency condition satisfied. So if we are on the edge between beta and some variant of omega, this is of course satisfied because this double ditch additional term is 0 on these edges. But of course it is present when we are on omega variant, and this is fine because we do not never stay on omega. This is for us forbidden state. So I will repeat, we do not want EC, the evolution consistency, to be satisfied on the edge omega 1, omega 2. But we can see that the double ditch there is in a very similar form as the standard double ones. It is eta y, eta I squared, eta j squared. So we can do the thing that if we reduce, we still have just three phases, 1 beta, 2 omega. If we reduce to the case where eta 0 is 0, so there are just two variants of omega, so it means we are on the edge. The interface energy looks like this. So here we added the double ditch term, and we can compare it with the effective interface thickness, and we can compare it with the standard double well interface energy containing the interface effective interface thickness and effective interface energy density. And if we do it, we can find out that the effective interface energy density scales with the square root of lambda, and the interface effective interface thickness scales with 1 over square root of lambda, which means that by increasing lambda, we can effectively increase the interface thickness parameter, interface energy density parameter, and still having satisfied the positive definiteness condition. So how we proceed? So we choose, I did not recombine it, we choose the interface thickness parameters, gamma omega, omega, gamma beta, omega, 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 L beta, omega. From this, we compute kappa i's and epsilon i's. We do it such that the positive definiteness is satisfied. And then we add the double ditch there with some lambda parameter positive, and we increase it such that there will be big enough hill which will prevent the appearance of direct interface between some variance of omega. And effectively, the gamma omega omega can be as large as possible. Of course, by adding the double ditch term into the interface energy, if lambda is too big, for example, 1 million, it is not computable. But so it has to be reasonable, but the experiments show that 100 is enough. So now I will come to the most difficult part, and this is the chemical energy. So again, we will start with just two phases where you know how to do it. So typically for the chemical energy is scaled by a cubic polynomial, cubic in the volume fraction, and we want that if we are in the beta phase, meaning eta 1 equals to 0, this polynomial is equal to 0. If eta 1 is equal to 1, we want that we are in the omega phase, it is equal to 1, and we want that the derivatives in the pure phases and beta and omega are 0, which is for two phases the evolution consistency. If we are in the pure phase, we do not want that it spontaneously but by themselves move away. And what can be also observed is that the cubic polynomial is such that the polynomial applied to 1 minus eta 1 is 1 minus eta 1. So this is the property of this polynomial. If we have more than two phases, if we have n plus 1 phases, it is more complicated. So first of all, chemically, all omega variants are equivalent, which means that it needs to look like this. So the chemical energy is in this form, and so now we are trying to generalize the chemical energy from two phase to n plus 1 phase. And because they are chemically equivalent, we want that the sum of this unknown mixing function, the sum of this is to be equal to 1. And that is why we can express this as 1 minus h tilde eta 0. So if we do the generalization, so this h tilde is just the sum of the original cubic terms. H hat is the sum of the original cubic terms, and if we insert here, we get that the sum of h tilde eta I going from 0 to n is equal to 1. So it makes the all omega variants energetically equivalent from the chemical point of view. So this is how it looks like, and as I said, so we want that the EC condition, the evolution consistency condition, is satisfied. If you insert it into the governing equations and you do quite a lot of calculations, you find out that this does not satisfy the EC consistency. But of course, by adding the double ditch on the edges between beta and omega i's, it improves the approximation of the energy consistency. You can easily think about this. So in the ternary plot, if you are on this edge and here you have a big valley coming from the double ditch, so if you move slightly, it will go back because of the valley, but it will be just approximate. So we found some mixing. We call it elliptic mixing. I talked already once about this. I simplified it as much as possible because this mixing has some other problems. But just for simplicity, we created this elliptic mixing. So it is called elliptic because if we take this effective volume fraction eta to be constant, so it is a surface of the rotational ellipsoid, and we want that the isolines have the same angle, so the contact angle between this edge and the isoline of the ellipsis is everywhere the same, which is the graphical meaning of the evolution consistency of our model. Unfortunately, we need to add additional two non-smooth functions to this elliptic mixing, because we want to flatten it here on this edge to satisfy that the omega variants are chemically equivalent, and also we need to add something here because if we do it in this way, so there are some extra minima where the model is finishing. So it is quite complicated to implement it, and unfortunately, Newton solver has quite big problem with this implementation. So now we are in the stage that we are using the chemical mixing, the chemical mixing I showed on the previous slide with large enough lambda parameter. So now I will come to the numerical experiments. So everything was implemented in 5 days. We use the backward order with some heuristic adaptive time stepping. Typically, we complete the problems at the beginning just in 1 dimension. So we discretize the domain with lines. In 2D, it is incorrect with quads, and in 3D, it is with hexahedra. Everything is linear or linear elements. Then we are using in 1 dimensions now Newton with the full step. For 2D and 3D, now we switch to the line search. And as a solver, so in 1D this is cheap, we are just using the direct solver mouse, and we are still playing with this. So for these problems, now we switch for some time to AMG, to the algebraic multiplicity. And extremely experimentally in engineering way, we tune some of the parameters such that it works as best as possible. So here, this is the first experiment. So lambda 0 means there is no double edge, and the chemical energy is very small, very close to 0. And here in the simulation, this is the initial condition, so it is perturbed by some noise, and we have just 3 phases, beta and 2 valence of omega. And here is the ternary plot. So you can see that in the beginning, it was in the pure phases, beta omegas, and in the middle, so that is exactly 1/2, 1/2. And the steady solution is the following. So the red line is 1 omega, the green line is the other omega, and the black line is beta. And you can see that even the chemical energy was very small. We have almost the contact between 2 different variants of omega. Now, there is some small beta in between, but quite small. If we make the absolute value of delta G larger, so if we go to minus 0.07, and still no double digit, all beta disappears, and we have only just pure omega 1 or omega 2, or we are on this edge omega 1, omega 2, which means that we have the direct contact between omega 1 and omega 2. Also, even such energy is bad, and if we make it even lower, of course, it will not get better. Everything falls immediately down to the edge omega 1, omega 2. So we will use our double ditch. So we keep this delta G and we use very small double digit 0.2. And what we can see a small amount of beta between two variants of omega. So in the energetical landscape, if you want to go from omega 1 to omega 2, we are going in this way. So this is still quite far from beta, not very good. So we increase it even more to lambda equals to 5. Then the trajectory is closer to beta. So already here you can see some beta between two variants of omega. And if we increase it to lambda equals to 100, so still there is no problem with Newton solver. So clearly there is some beta phase between two variants of omega. So this was in 1D and 1 beta and 2 omegas. So now this is simulation with 1 beta and 4 omegas. And the same parameters, and again you can see that in the steady solution we have two variants of omega and beta in between. So this works quite fine. Then we computed the problem in 2D. The initial condition was such that we had three variants of omega in contact. And during the evolution, beta, which is great, appears in between them and it separates the different variants of omega. Here we are using this simplified mixing because if we use this complicated elliptic mixing, it is much more difficult to solve the problem, and even it satisfies the EC condition on the paper. We are getting negative minimal values. So here you can see that slightly we are not satisfied with the physical range. So the all volume fractions are not exactly between 0 and 1, but here minimum is minus 0.01. And of course, energetically, it is clear that it wants to go to at very large time. It wants to go just to one variant of omega. So I can also comment on the non-symmetry. Even the initial condition is not non-symmetric. So there are almost three pure phases of omegas at the beginning, but it is also perturbed by noise, which is non-symmetric. So it is not just because of some numerical errors, but the initial condition was not perfectly symmetric. And the last thing that I can show you is the simulation in 3 dimensions. So here the chemical energy is not constant as in all previous cases. So here the chemical energy is constant in time, but it depends on the space, and it is computed somehow realistically based on the also it is more complicated. So in titanium alloys, there are not just atoms of titan, but there are also some extra atoms. There are atoms of molybdenum, and the molybdenum atoms decide if how much the beta phase or omega phase is preferable, changing the delta G. They are somehow distributed in the space and making the distribution of the delta G non-constant. So if we use this real non-constant delta G, and we also add to the free energy the elastic energy, so here we just assume that it is linear elasticity, also some new part. EL squared, something like this, and this EL. So this is the strain coming from the total strain minus the transformation strain, and the transformation strain is computed if this is a function of e plus 0 to eta n. So if we add also this information, so we are getting this result. So here this is again computed in the periodic domain. And the structure, so here because he was satisfied with this, he said that it is something he would assume that it is observable. No, but don't forget, it is just 50 nanometers. It is very small even for the microscope. So
Location of molybdenum is somehow random, or
no, it is not random. This is based on some calculation that was done by the and this will not be part of this result. So I don't remember the details about this. Also, it is a result. The position of the molybdenum atoms is based on some other calculation. By minimizing the molecular energy. So this is the final slide. So we were able to derive a model that is capable of arbitrarily strong total spreading case. I will repeat it again from the beginning. In the total spreading case, we want that some phases cannot be in contact, whatever happens, and it means that the first or the zero parameter kappa 0 in front of gradient theta 0 squared is negative. So we cannot for free have the positive definiteness of this gradient part of the energy, and we need to compensate it by the other kappas, making the relation between the interface energy density gamma omega omega and gamma beta omega. So we cannot make gamma omega omega arbitrarily larger than gamma beta. So that is why we need to add some new terms into the model. We call it the double ditch term, and using this double ditch term, we effectively increase the interface energy density between gamma omega omega as much as we wish. This still satisfies the evolution consistency. This what we wanted from the model. But still somehow relaxed. We want that this evolution consistency is satisfied only on the edges beta omegas, not on omega omega. Whenever we have a point on omega omega edge, we want to kick it away close to beta. And we also added complex electric mixing for the model that satisfies the evolution consistency condition. However, there are some implementation issues that make it quite difficult to use it, and we do not see big advantages for this mixing. So that is all. Thank you. And